So is the algorithm itself clear? We round, we scale, we run this black box that we know works. Again, I haven't yet opened the black box here, I will do that. Okay? So all we want to do now is make sure that the quality of the answer we get is reasonable. Yeah? Okay. Don't tell me it's working. I guess it is. Okay. All right, so the first thing I want to prove today is, so we want to show that we get a good approximation. Okay? And specifically, what we want to say is that if this is the answer we get from our algorithm here, our answer is A, and then there's the optimal solution. Remember, we're maximizing. So we want the algorithm to be close to the optimal solution. So we want it that, we want this to be more than something like this, right? Again, think of it this way. Think of epsilon as, say, I don't know, 0.1. What we're saying is that we want the algorithm value to be more than 0.9 times opt. We know that the algorithm can be not any more than opt. That's the definition of the optimal solution. But we want it to be close, so within 10% of the optimal solution. That's what this is saying. So this is what we'd like to prove. And if we can prove this, we've done something very cool. Because we're now saying, no matter what epsilon you give me, I can give you this guarantee. It'll just take long. And this is different from any other approximation that we've seen in the past few lectures. Okay? All right. So how do we do this? So this turns out is going to be actually quite simple to show. It's just a series of inequalities. So I'm just going to make sure I get them all right so I can, because it's very dangerous to do inequalities on live without checking. So what we're going to say is this. So remember what our algorithm does. It does scaling and rounding, and then it finds the exact answer. So our algorithm is optimal on the v hats. So let me write this down. So our algorithm right? In other words, if I take an instance of knapsack where I only have the values being the v hats, right, then our algorithm is optimal because it runs the exact algorithm for this problem. It's also, by the same argument, optimal for this. Do you see why that's true? Remember, the v tildes were the rounded versions of the original input. Do you see why that's true? So why is our algorithm optimal for the rounded versions, rounded values from the input? Yes?
Because we're finding the solution using dynamic programming. We're doing the...
Right, but to be precise, we're running dynamic programming on the hatted values, not on the tilde values. Why is it optimal for the tilde values as well? Yeah, Victor.
Is it because they're just off by a factor b?
They're off by, in fact, they're off exactly by a factor b. It's not like, oh, it's less than a factor b. It is exactly that. Every v tilde is v hat times b. It's not less than equal to this times b. It's exactly that. Right? It's like saying I have all my values were 10, 20, 30, 40. I divide it by 10. I take the instances 1, 2, 3, 4, and I got the exact solution for this. Obviously, I get the exact solution for 10, 20, 30, 40. It's just a factor of b. Right? If I change my currency, it doesn't matter. I get the same answer. That's essentially what's going on here. So we know that we get the optimal solution for the v tildes. But what we want is a nearly optimal solution for the v's without the term. And that's the question we have to answer. Okay? All right. So, let's imagine, again, that's always we do this, right? Let's imagine the optimal solution. So every solution to the knapsack problem is a subset of the objects. Say I'm going to pick these paintings to put in my backpack. Right? So the optimal solution is some other subset. Let's say some subset of 1 through n, objects 1 through objects n. So let's say the optimal solution to the original problem. Okay? So let's say the optimal solution is denoted, optimal solution is produced by picking some set S star. Okay, we'll put the star to know this was the optimal solution for the original problem. And let's say we, A, picks the set S. We pick something different, right? But not necessarily when I pick the optimal. We just want to pick something else. What we want to do is relate the two costs. In particular, we want to relate these two quantities. And you see that? The optimal value, the cost of the solution is exactly this by definition. You take all the items the optimal picks, you add up their value. The cost of our solution, A, is that one. You take all the items you pick and you add up their values. Right? In order to show that one, we have to essentially relate these two things. That's going to be our goal. How do we connect what we picked to what the optimal solution picked? Okay? Okay. And what do we know? We know one thing for sure, that we were optimal for the v hats, and the v tildes. Can we use that fact somehow? As a matter of fact, we can. So here's what we can say. So step 1. So we know this to be true. We just argue this is true. What does that mean for our instance? We know that we can write this. See this? We know that we were optimal for the tilde values. So whatever solution opt produces is opt for the v, but not for the tildes. When you get to the tilde case, the rounded case, we are actually better. And that's what I'm saying there. Our solution, when you sum over s, is better than the opt solution summed over s star for the tildes. That makes sense? Because opt is opt for the v's, not for the tilde v's. Okay? Alright, but we also know that the tildes and the regular values are close, right? We also know, for example, that vi is less than equal to vi tilde, which is less than equal to vi plus b. Just by the definition of rounding, right? If you divide by b, take the ceiling and then multiply by b, everything is going to be within an additive b, right? If b was 10, everything's going to be within 10 of its rounded value. Right? 21 will go to 30 in the worst case. 20.1 will go to 30, but that's okay. Right? Can we put these two things together to give us something that we can talk about? Because our goal here is to replace all these tildes by just regular v's. That's what we want to do. So here's what we can say. So let's look at the optimal solution. We want to compare, remember, we want to compare the optimal solution. So that's I summed over S star, VI. Right? But we know this is less than equal to right, by the first part of the second inequality. Right? But by the first inequality up there, right? Wait. Oh, sorry. I got something wrong here, didn't I? No one caught me on this. Why did no one catch me on this? That's not a good sign if no one caught me on this. It means I'm not making any sense to anyone. This is wrong.
I was
Huh?
I was confused.
Ah, you were confused and you thought you were wrong. I was the one who was wrong. So speak up. Yeah. So why were you confused?
It's because, wait, let's see. So that's the set of the V tilde, and that's the set for the V, the optimal for the V.
Right.
So we're trying to maximize V.
And,
Yeah, go ahead. Go ahead.
right, I'm trying.
Yeah, it's okay. Take your time. This is good.
Okay. And yeah, so we know that we're for the V tilde, when we
We're
solve the
better.
problem for the V tilde, we're better than the V.
But in this case, better means
Better means greater.
greater.
Sometimes,
Exactly.
sometimes better means the other way.
Sometimes better means the other way. You got to keep that
That's
straight in your
why-
head. I didn't keep it straight in my head, so I can't blame anyone else for not keeping it larger.
Yeah.
You're right. For this case, we were better, so this should have been this.
Yeah.
Good. But yeah, if you're confused, you're most likely I'm wrong. So don't hesitate to speak up. So, yeah. All right. Okay. Things are back to normal. So we have this inequality chain going on here, and now I will apply the correct version of the first inequality, and say that this sum is less than that sum. Notice what I'm doing. So it's like those word games where you have the first word and the last word, and you just want to change letters one by one to get from one to the other, always keeping a valid word. I have the starting point here. I have the ending point. I want sum of vi from I and s, and I have sum of get from one to the other using valid inequalities. That's a game we're playing here. So we've got one step over. So I've gone from this to the tildes, which is good. I can get from s star to s using that. So I'm going to write that out here. Okay, but now what do I do? I want to get to the tildes while keeping the s. What other information can I use now? What do you think? What should I do next? Do I have a way of getting rid of the tildes? Yeah?
Well, we know that VI told us less than VI plus B.
Very good. So we can plug that in here. We can replace this VI by that and keep the inequality direction in the same way. So this becomes less than equal to sigma I belonging to S, VI plus B, right? Right? Which is, now we don't know how big S is, but what's the largest value? Because we're doing less than equal to, how big could S be in the worst case?
All of the elements.
So how many items could be in S?
N.
N. So then I'm going to write this. I'm going to write this here. So this number becomes and this is going to be back. I just collapse that chain of inequalities. And now I actually have a relationship between the optimal solution to the problem and my solution to the problem. So first of all, a sanity check. Does this help us? Well, what is this saying? If we translate this in English, right, we're saying opt is less than equal to something plus us. So okay, this is us, and opt is somewhere above us because opt is going to be better, but it's less than something. In other words, opt is not going to go running off like a train. It's less than something above us, right? So if you think pictorially, we are here, opt is somewhere here. It can't go any higher. This is what you want, right? Because what we're saying is that opt is not too far away from us. That's exactly what you're going to be able to use somehow to get an answer. So we're on the right track here. See what I'm saying? We have somehow been able to bound opt above us by a certain amount. This is the equivalent of the lower bound. We have an upper bound. We have now produced an upper bound on opt in terms of our algorithm. Yes?
So this is just basically saying that the more elements we have and the more we round and scale, that error is going to accumulate.
And that kind of makes sense, right? If you do more rounding, you're going to increase the error. But luckily, we've already chosen the error up front. We're going to have to plug it in now and see what happens. But yeah, that's the basic idea. Make sense? let us now substitute the value b. So this is going to seem like magic when I put this in, it all kind of works, or hopefully it works. But of course, you should think of it not like magic, but that we started off with this, and then we figured out what b needs to be to make the whole thing work. In fact, maybe let's do it that way. Let's figure out what b needs to be to make this work. Okay. So let me write this inequality again. So, let's see, okay. What we want, remember, what is our goal here? If you remember what my goal was, and this goes back a few pages here, this was our goal. We want the algorithm to be greater than or equal to 1 minus epsilon times opt. If you kind of flip it around, and if you use this approximation that 1 divided by 1 minus epsilon is roughly 1 plus epsilon by the binomial theorem, you can rewrite this expression as you want the opt to be, so this is opt. Right, so what you're saying, this is opt. What you'd like to see, you want this whole thing to look like this is what you want. If you're able to get to this, then you have done what you achieved, because if you flip it to the other side, you're saying the algorithm is at least 1 minus epsilon times opt. So the opt is not much more than the algorithm. So the question is, how do we go from that nb plus a to this? Right? So we know that, we want this term here. So we kind of want, I'm going to put a bunch of question marks here. These are not equations, but things we would like to see. We'd like to see that nb plus a kind of looks like a plus epsilon a, which is 1 plus epsilon times a. Okay? Okay, so we got the a cancelling out. So we kind of want n times b to look like epsilon times a. Right? So we kind of want to look like, we want b to sort of look like epsilon over n times a. Right? In particular, we want b to be less than or equal to this quantity. So we would like b to be less than or equal to this quantity. And then everything will be fine. So I'm showing you how you reverse engineer what you need for the scaling value. Because we don't know what the scaling value should be. We just know it needs to look like this for our algorithm to work. Now here's what we do know. Right? We know that the algorithm value, so put this here. So we know that a is equal to sum of I belonging to S vi. We know this for sure, right? In particular, we assume that, okay, so no single painting is too big to fit in the knapsack. What just happened? Why are you even twitching? Huh. Okay. Ghosts. So we assume that every single item fits in the knapsack, and therefore we assume that so remember, V star was the largest value item. So why does that inequality follow from the assumption? Because if every single item can fit in the knapsack by itself, at least pick that value. Can at least pick one item. But a one item solution could very well be the maximum value item solution. So my actual solution can only be more than that. I mean, it can be equal, but it's going to be greater than or equal to that. Yes?
So for opt, is less than or equal to nb plus a?
Yes. That's what I get. That's what I can say that for sure once I do this rounding strategy.
Because doesn't opt have to be greater? Because we're...
Yeah, but NB, so think of, okay, algorithm is here.
Yeah.
NB is a positive number.
Oh, okay.
So opt is definitely greater than A, that's for sure. But it's not much greater. It's limited in how much greater it can be. So definitely, if we draw this pictorial,
Opt is greater than a?
Opt is always greater than A, right? Because opt is opt.
Oh, and B is a,
Is a number, just a number.
oh, okay.
So pictorially what we're saying is that this is the algorithm. So let's draw a picture here, right? So this is the algorithm here. This is what we got. Opt is somewhere above here. Opt could be anywhere in the space here, right?
Yeah.
That's we know for sure. But what this is telling us that no. It could be anywhere, but it can't be higher than this, where this is NP.
Okay.
Opt cannot escape from the algorithm by too much.
Okay.
This is a property of our algorithm. We've been clever enough to design an algorithm by doing this rounding so that opt can't escape too far away from us. And that's the key to making this whole thing work. All right? Because we did the rounding carefully, and so we said, okay, look, we're rounding, but it's not going to change it too much, and now we run our exact algorithm, which is optimal. So with those inequalities, we were able to say opt can't get too far away. And now we just want to make the statement precise. Does that make sense?
Yeah.
Okay.
So,
Yes.
so we are trying to quantify how much rounding we are doing so that
How much error we're going to get from that?
Exactly.
Yes, exactly. That's why we're trying to figure out what B needs to be.
So
So we're trying to figure out what rounding parameter we need to make sure our error is not too
so
high.
that the bound is really
Exactly. So we're trying to figure out what B should be. I mean, I told you what B was, but I want to tell you how I got to that point. Right? Next, yes?
So can you remind me like exactly what S and S are?
Yes, S is the set of items produced by our solution. S star is the set of items produced by the optimal solution, which we don't know. Right, so some of the values of in the optimal bag is opt. The sum of the values in our bag is our solution. Okay? Any other questions? It's all good. Very good. Yeah.
When did you make the assumption that any item can fit in the bag? Just now, or was that?
Just now. It did not change the algorithm at all, but it's sort of a simplifying assumption. And it's not a restricting assumption, because suppose you have an input for which this is not true in the bag. You can't pick them anyway, throw them out. What's left? Items that can fit in the bag. Your problem in any way at all. No solution is ever going to pick those items because they don't fit. So when I say it's an assumption, but it really isn't. Because it doesn't change your problem in any way, it doesn't change the structure of your solution in any way. It's a simplifying point you can make just to make this analysis work. Yeah.
So divided by this.
Every individual item.
Oh.
Yes. Yeah. Okay. So because we know that every individual item must fit in the bag, otherwise you could just throw it away. By inspection, if my item weight is more than W, throw it away as a pre-processing step. Right? We know that the optimal solution that any solution we produce is at least as good as picking one item, and in particular, it's at least as good as picking the most valuable item. So we know this is true. Right? Therefore, if I set B equal to epsilon V star over N, I am guaranteed that this is less than or equal to epsilon over N times A. Because of this argument here. I didn't know A. If I knew A, that would be great, but that's the whole problem. I don't know A when I just fix B, right? I have to fix B before the algorithm starts. I don't know the value of A. But I can find this proxy for A, V star, which is good enough. And in fact, that's exactly what we picked. It was a factor of 2. And that's it. That's the whole algorithm right there for you. We have now shown that by picking B to be this value, it is less than or equal to this value, which means that now we know the optimal solution is less than 1 plus epsilon times our solution. We've already shown that the running time of the algorithm is reasonable. It's n cubed over epsilon, assuming the black box. This is done. QE.
So this is like, you're assuming you can pick the highest value density item for everything?
I have my input, not density, just the value, highest value item. So I have my input. Each item has a weight and a value. I scan them all. Okay? I say, oh, this is the largest value single item. I write down its value, V star. I define my B to be epsilon times V star divided by N. I use that to round. That those items I picked, say, here's my solution. And what this proves is that that solution is going to be epsilon times.
So this means that the more items we have, the smaller our error will be?
No, the error is always going to be epsilon.
Because as n gets larger,
But epsilon doesn't change. Right? The rounding parameter changes, but epsilon stays the same. Epsilon is given to you ahead of time, right? I want 1% error. I plug that into this value to get b. The rounding parameter will change, yes. Right? Epsilon times b star divided by n will change as b gets larger. But the error is always going to be 1 plus epsilon.
okay.
Right?
I'm just kind of confused on how to interpret like n growing in that equation that we had.
It just means that your rounding scale parameter gets smaller.
Okay.
Right? So if your maximum item value was 10, epsilon was 0.1, n was 10. So you're saying b is 0.1. So you take precisions up to that. So you essentially you divide everything by 0.1 or into the rounding. If your n goes to 100, your rounding parameter becomes 0.01, but epsilon does not change. The guarantee you get is still the same. You have to, essentially if n gets larger, you round at a different scale to get the same error. If you round the same scale, then your error will change. Something will change it, right? I mean, if you keep this fixed and keep this fixed, then this will change. If you keep this fixed and change this, then this will change. And so on. Yes?
I'm a little confused about the A is greater than or equal to V star. I know that V star represents the maximum value
Of a single item.
of the single item.
Yes.
But how do you guarantee that?
This is one
So
that
we assume that the knapsack fits every single item
by itself.
by itself.
Yeah.
But how do you know that? So what if you pick so we produce something that's like less than the maximum value, but only one thing fits in the.
Okay. Remember that the scaling rounding stuff, right? All this, the scaling rounding that we're doing in the algorithm, right? Is going to so let me say this. Consider V star, okay? And consider any other item in my set, which is less than V star. Let's say I round these two. What can happen? They could round up to different values, but they could round to the same value. Would they ever round to this? Right? Okay. So once we have rounded, the thing that was maximum in my original set is still the maximum in my tilde set. Okay? Okay, step one. Step two. Once we get to the tilde set, we are actually producing the optimal answer. We only argue that we get the optimal solution for the tildes because they're just scale rounded and we just run the exact algorithm. So we get the exact answer for the tildes. Okay. Look at that solution now. Suppose that solution cost, the value was less than the value of the single largest item. Why didn't I pick it? I'm supposed to be optimal. I should have picked that one.
Okay.
Right?
So guarantee you always pick.
Because every single item could be picked, it gives you a feasible solution. We know that in the worst comes to worst, you can always pick that one item. And if you don't, it's because you got something even better. And that's what I'm saying. And the crux is that the rounding doesn't change who's the max item. Right? It might make more things max, but that's okay. Make sense?
Yeah.
So if the max item is much, much larger than
Everything else.
that'll make B go up, but it
Yes.
wouldn't change.
You won't change the quality of the solution you produce.
Okay.
That is correct. You won't change the quality of the solution. At
But
all.
would it increase the runtime, I guess?
A little bit. It depends on how you do it.
Oh.
To do the division, the V divided by B floor ceiling operation. But that's it. Once you actually get the final rounded scaled answer and run the exact algorithm, even that doesn't change. Because that max value is n over epsilon. We always said that.
Okay.
Right? So the time it takes to convert your initial instance to that rounded scaled instance might increase a little. Yeah.
Can I see the slide? So, I have an intuition on the first equation. It sort of looks to me like it says the sum over our solution is bigger than.
Yes, for the tilde values. Because what was our algorithm? our algorithm was, oh,
Your algorithm finds the optimal on the tilde values.
that's right. That's why this works. Because we're optimal for the tilde values, we can say that first equation. Otherwise we cannot.
Actually, can you say it?
No, because opt is opt for the original input. Once you round things up, the numbers change a little bit. You don't know what's going on. Right? Yeah? Other questions? Yeah.
So on the previous page, we were trying to go for 1 minus epsilon, right?
Yeah.
And did we end up with that, or did we end up with 1 plus epsilon?
So no, what I did was the following. This is a standard trick. If for small enough epsilon, it's always the case here. Let's see, what I want. I wanted algorithm greater than equal to 1 minus epsilon times opt. If you flip it around, you get a over 1 minus epsilon less than equal to opt, greater than equal to opt, right? By the binomial theorem, 1 minus epsilon to the minus 1 can be approximated by 1 minus 1 times epsilon, which is 1 plus epsilon. So 1 plus x to the n, if x is very small, is roughly 1 plus n times x. It's the first term of the binomial expansion of 1 plus x. So the trick we often use is that you can rewrite this expression as a times 1 plus epsilon is greater than equal to opt. And that's what we proved. Right? Because opt is less than equal to 1 plus epsilon times opt. So it's just a convenience. You could have done this in terms of opt minus nb, it would have worked fine. But this is often a trick you do too. This works for small epsilon. If epsilon is huge, the binomial expansion approximation doesn't work very well. Yeah.
So I got a little hung up by the fact that we just need some b that's smaller
Yes.
than epsilon over n times a. We could have just picked 1 instead of b star, right? And then it would just be epsilon over n, but then that wouldn't buy you anything, right?
What would happen if you do that?
You're going to have a value less than 1.
The error will not change.
The error will not change.
What will go wrong?
Your maximum value will get bigger,
And then what will happen?
and then your complexity gets bigger.
Exactly. So there's actually a balance, there's a delicate balance going on here. I hid that part of it. But there's a balance here in choosing B. You want B to be small to make the error go down. You want B to be big to scale things down so your running time goes down. And the sweet spot where the thing pushing you down, the thing pushing you up meet is here. That's the trick that's going on. And all of these algorithms, all of these kinds of approximations, and when you read your project papers, you should look for this. There's always some kind of balance going on. When you see a result saying, our algorithm takes time n to the 7 over 11 divided by epsilon to the 2.5, it's because you're playing some balance game, and that's a sweet spot where the balance happens.
So v star is the best we can do as a lower bound for a?
Essentially, if you want to get the right hand, because you want to get rid of the v star in the dependency of the other hand. Yeah. So kind of, I cheated a little bit by claiming that, oh, it just works. Actually, it's a result of a balancing act. You could have made b a lot smaller here, but it would have killed you on the right hand. That's always going to be the case, okay? It's always true that there's some natural tension and trade-off. And a lot of algorithm design is about changing the trade-off points so that you get a better bound of what you want. Between the complexity, the error, or whatever other parameters you're trying to play with. Okay, let's take a 3-minute break just to digest. That's why it's because it's there. Well, to be fair, I said we're the normal. All right, shall we continue? There is one last piece to this puzzle before we can put this whole thing to rest. I gave you a black box and I haven't opened the black box yet. Plane. Everything rests on this plane, right? This was the thing that was driving our approximation algorithm. Because we said, oh, let's just round it, scale it, and run this black box. And everything works because we're optimal. If we can't produce this, everything falls apart. So I need to give you this. This actually is a relatively simple dynamic programming. This again is a common theme in these things that you usually have some kind of dynamic programming solution and you adapt it. And the way to think about this is that, as always, what we want to do is have subproblems. So the subproblems, so the solution is a dynamic program. And so you have subproblems. So we have one subproblem which will have two parameters. It will have a parameter I and a target value V. And the value is the, let's see, it is the minimum weight needed to get value V using items 1, items 1 through I. So I had outlined a dynamic program for knapsack earlier, and there I said the state was I comma W, and that was the maximum value you can get if you have items 1 through I and weight W. Here I'm flipping it around and saying, fix a set of items 1 through I and a target value V. What is the minimum weight that I need to get that? Okay. How will you find the optimal knapsack value from this dynamic program? Suppose I could fill up all the entries in this table, right? There's a whole bunch of entries in this table. Suppose I could fill them all up. How would I find the actual best solution? What would I do? Yeah?
You just consider an item either being in the optimal solution or not.
No, sorry. You're telling me how to solve it. We'll get to that. What I'm saying is, suppose I did fill up the whole table. I had for every value of I and every value of V, I filled out the correct value. How will I actually get the optimal solution? So in other words, I have this gigantic table now, right? So I have this table. So there's V going up here, and there's I going this way. I fill up all the entries. So I have this table, 1 to n, right? And I fill up all the entries in this table. How am I going to figure out what the actual optimal value is from this table?
Find the highest up on the v-axis W value that still fits within your budget.
Very good. So you look at the highest value of V. You look at actually the last column because you want to use all the items. But that's correct, right?
Okay.
So you look at the last column and you look at the value of V you get, keep going up as high as you can, while the value in that entry is still less than equal to W. So maybe this has got a 1, this has got a 10, this has got a 15, this has got a 20. This is the weight you carry. And let's say W was equal to 16. Then you say, okay, this value of V corresponding to 15, whatever value of V that was, that's my optimal value. So once I have this table, I can find the optimal solution. That's easy, right? And as usual, you can track back to see which items you picked. That's not a big problem. The question is, how do you fill up this dynamic program in the first place? How do you fill up this table? And that's where we have to sort of define these subproblems and figure out how to do this recursively. So how do we do this here? And this is where I think Daniel was trying to explain how we're going to do it. You want to go ahead and tell us now what you're going to do?
Well, it's the same as before, right? For every item, we look at whether, we consider the cases where.
So let me do this on another page here. So to start with backwards, since we like to do things backwards. Okay, so start with the last item. So every dynamic program starts like this. Either the last item is in the set or it's not in the set. Suppose it's in the set. Then what do you do? So suppose the item n belonged to the optimal solution, right? Then what are you looking for? Then the value is going to be, then the actual value, let's see. So, how do I say this? Okay, so opt n comma v is going to be equal to wn, what's it going to be equal to? The weight of this plus, plus right? If you pick if the last item happened to be in the set, then you have to, then of course that weight contributes to the total weight. Then you look at the best solution you get from the previous n minus 1 items with the value of v minus vn, because you want to get a target value v, and you add that weight to this, right? So this is if, yeah, so if this one. If n is not an opt, then opt n comma v is equal to what?
Opt n minus 1v.
Yeah, because you didn't pick it. Right? And of course, if one edge case is if actually that's fine. That's it. And so basically, your dynamic program opt n comma v is equal to the max, or the min, because you're looking for the minimum weight of opt n minus 1 comma v plus so very much like the previous dynamic program that we saw, which is in terms of values and not in terms of weights, and doing a min instead of max. And so you should convince yourself that this can be solved using, you build up the table. As always with dynamic programming, you decide recursively, but you solve bottom up. And so you just go from the beginning, you work your way up to the top. How many entries are there in this table? Well, there are n columns, one for each item. But the number of the height is the total value possible. What is the maximum total value possible? It's not V star. V star is the value of one item. What's the total value possible? Worst case, it could be n times V star, right? Every item could have the maximum value, right? So V, capital V is less than or equal to n times V star. We'll assume these are all integers, so that you have discrete values. So the total size of the table n times n V star. And you can see from this recursion that it takes you a constant time to fill in any particular entry of the table. You just look at two other entries and take the smaller one. So the table size is n squared V star. It takes constant time to update any item in the table. So the overall running time of this dynamic program is n squared V star as promised. Any questions about this? So this finally completes the entire polynomial time approximation scheme for the knapsack problem. We had a rounding scheme, and the rounding plus that whole scheme, and said this is the running time of the scheme, assuming the black box, and this is the error you get, and then I finally gave the black box. Yes?
So does the bit size of V star matter then?
Sorry?
Does the bit size of V star matter?
It does matter.
So is it still exponential?
This is exponential. I said that. This is an exponential time algorithm.
Okay.
But we rounded and scaled our input so that V star became very small. And this is again, so So any other questions about this? So the point, yeah, sorry.
So if you can't get exactly the value v, what do you put in that entry?
I don't follow.
So if you go back to the previous page, minimum weight needed to get exactly the value v using items that, or at least value v. Say all of your values were even numbers. You put something.
So it doesn't matter because I'm using all possible values. So if I can't get value v, I can think about value v plus 1. So these will be empty in some sense.
So okay.
Right. So it doesn't really matter. You could change that to less greater than equal to v, but that just no, you want exactly v because you're gonna look at every single value v. Yeah, that's gonna be some value of v, right? Right below it, which was in any case you'd be looking 2 rows down to subtract, right? Because you're going to be looking at, if you're going to look at this here, this is going to be 2 rows down at least if everything's even. So you're always going to leave your odd rows blank anyway. So that won't affect. So that'll so you do want exactly. Yeah.
Then it
So,
says,
okay. Yeah. Go ahead. I'll get yes.
it says suppose like n is part of opt.
Sorry.
You said it says that suppose n is part of the opt.
The last item is part. So we're in any dynamic program, the way you start off is by saying, okay, recursively, what happened to the last item? Was it in the optimal solution or not? We don't know, but there are 2 cases. Either it is or it isn't. In one case, the value of the optimal solution will be defined by that. So we're going to just try both and take the best one.
So n is just some item.
The last item, yeah, items 1 through n.
Okay.
Yeah. Yes, you had a question?
Back to what you were saying before, did you say the V's where you have every single possible value of V?
Yes.
So the
From 1 to n times v star.
1 to n.
Integer values, let's say.
Okay.
Yeah. The idea here, the key idea, right here, and as it turns out in many approximation schemes. So we've seen, this is going to be the last time we talk about approximations for a little while. We'll get back to it later, but we're going to go away from it for a while. So I want to just say something before we leave. We've seen different ways of constructing an approximation algorithm. And they all boil down to a couple of different ideas. So the basic idea that goes through everything is this idea, and again, I'll explain this in the language of minimization, but it works for maximization as long as you reverse your inequalities and do it correctly, is that you want to find some bound. So it's either an upper or a lower bound on the optimal solution. Okay, you have to do that. Without that, you have nothing. Okay. And then you want to somehow connect an algorithm to this bound. This is the 2-step dance of every approximation algorithm you'll ever see. Get some bound on the optimal solution and connect what you're doing to that bound. That's also where all the creativity lies, where all the mystery of these things lie. What kind of how do you come up with something? And how do you make an algorithm that takes advantage of it? It's all. Now, how you do this in specific cases varies, right? And so for some problems, it turns out, and we'll see this a little later on, I keep promising this, and we will get to this, is that given a problem, you can send it into a black box. It's like magic. For a problem that can be expressed this way, you get a lower bound for free. And then it's just a question of designing the algorithm to take advantage of the lower bound. When you talk about linear programming, we'll talk more about this. Okay. Sometimes you're not that lucky. You have to think a bit harder. You can't quite express it in terms of this black box. So you sort of think. That's how much harder it is. Sometimes you do have an exact solution to the problem, but it's horribly inefficient. Right? It's a crappy solution. It takes exponential time. But do not despair. Sometimes you can transform your input to some modified input and then run it through an exact black box. So this is an exact. And there's a large percentage of approximation algorithms that work this way. Don't try to come up with a new algorithm. Use the one you have, but change your input so the algorithm runs efficiently. Like we just did for knapsack. There are other ways you can think about designing approximation algorithms. They all boil into those first two steps. And a lot of them will boil into one of these two things. Using a black box from the lower bound and reasoning about it, or using some way to modify input to apply an exact black box. So when if ever you have to come up with some kind of guaranteed approximation of a problem, these are some of the strategies you have to start thinking. Again, there's no formula here. There's no crank you can turn that outcomes thing. This is one of those things, that's why it's a more advanced topic. But these are some of the things you can try. And that's invariably what people will do when they first put pen to paper to think about it. And again, of course, in all of this, you could be deterministic, you could be randomized, all these things can change, and we'll see again sometimes how you to go from here back to there, use a randomized strategy, sometimes you can use a deterministic strategy. That's a separate orthogonal kind of concern. Then again, all the intuition you built up using about randomization can apply here as well, separately, once you have the question of how to design the algorithm. But this is how you have to think about it. This is what is different about approximations, that you're reasoning at a meta level about the properties of the optimal solution, which you don't normally do for a problem. You want to find a spanning tree, you just find it. You are actually reasoning about the optimal solution, but it's hidden, buried so carefully inside you don't see it. Whereas here you have to do this more explicitly. Yes?
Just wondering, are there times where you can change the input, like even when it doesn't seem obvious? So like, for instance, reset, like I'm not sure how you can change the input to use the bad algorithm.
Preset's an interesting case because you can take a brute force algorithm for 3-set and you can slightly modify it using randomization to get a slightly better algorithm. It's not much better. One way you can modify the input is, by, okay, so here's an example. Suppose you have a problem on a graph. You want to solve some hard problem on a graph. I don't know how to solve a hard problem on a graph, but I can solve this hard problem on a tree. So I say, okay, if my graph were a tree, I can solve this problem exactly. So how do I make my graph into a tree? It turns out there are ways of doing it. There are ways of taking a graph and converting it into a tree or a collection of trees that kind of approximate the properties of the graph. For example, suppose you're measuring distances in the graph. You can say, instead of measuring distances in the graph, I'm going to build a tree and measure distances along the tree. My distances will be off because they won't be right, but I can bound the error in the distances. Now I run my problem, my exact algorithm for the tree. It gets me the exact answer. It depends on the distances, but I knew the distances were off, but they weren't off by too much. Voila, I have an algorithm for it.
So I guess the question asked then is, for what inputs would the exact black box work well on, and then can I reasonably get from my input to that input?
And prove something about how the optimal solution will change in the process. Yes, exactly. And this is one example of it. Graphs and trees are another example of this. And so. Yes?
So when we're doing something like p tilde, in our case, we sort of just assume the black boxes and we know what our answer sort of looks like, or we want to get to. Generally, we have to play the trick with the p where we have to say, okay, this is what we want to get to, so this is what our black.
That often happens. So you don't have a black box. So you have some candidate p tilde, you say, okay, maybe I can design a black box that works. Oh, but I can design a black box that works with this. Can I get a new p tilde? Oh wait, that doesn't work. Go back and forth and finally. So I'm presenting to you what looks like a nice clean solution. This is the black box, this is the p tilde, and everything just works and we're all happy. But yes, there's a constant iteration going back and forth. You try something that gives you something like, you just get clues and you kind of keep refining and refining clues. More questions? So what I wanted to do, depending on how much time I had left after this, was to talk about the project. I feel like I don't have enough time to do justice. Here's what I wanted to do. I was going to take a paper, And I'll do this actually next time, so don't worry. No, not this one. This one. So I was running this paper, the one I mentioned to you before. And I was going to tell you, okay, suppose this were my project topic. This is the paper I chose for my project, what would I do? So I want to walk you through how you might view a paper like this. And by the way, you were asking about graphs and trees. This is the paper, coincidentally. So the geometry of graphs. It basically says how do you take a graph and map it to some nice geometry where things are easier to do. Anyway, I digress. So I won't do this today because we don't have a lot of time left. I'm going to do it next lecture. I want to spend some time taking, here's your project paper. How do you go about attacking the paper? How do you go about reading it? A paper is not, a story. You don't read it from beginning to end. You almost never do. Right? You spot check it. You read a bit of the abstract. You get stuck at 5 words into the abstract, like, okay, I don't know what that means. Like, okay, maybe not 5 words. Let's see. So what's the first word you get stuck at here? Anyone?
It's not visible.
Sorry?
It's not visible properly.
It's not visible. It isn't, is it? This lighting is kind of off.
Should be a bit darker.
Sorry?
Should be a bit darker. So.
Darker. I don't know if I can make it darker. I can try to make the screen darker. That doesn't affect the projecting darker. Okay. Well, okay, let me read. So, in this paper we develop, I'm starting from the second line. There's a reason why this paper is very old, the quality is bad, it's a postscript. In this paper we develop efficient algorithms for embedding graphs low dimensionally with a small distortion. There are a number of words here that don't make any sense, right? Okay, we know efficient algorithms. Embedding graphs, I don't know what that means. Low dimensionally, what is the dimension of a graph? Small distortion, what on earth does that mean? So if you start trying to read linearly and you get stuck with all these words, you're gonna go down. You'll spend 3 days in a rabbit hole on Wikipedia and you won't get anywhere. So what I want to talk about is how you try to go about reading papers like this, how you spot check them, go back and forth, read it over and over again, focus on one lemma, put the rest of the way. For those of you who had gotten an email from me about your project, and I know this paper, you must come and talk to me, okay, or at least email me. Some of you couldn't come and you emailed me and I emailed you back some suggestions. Please do that. I want to get this done by the end of this week. Okay? Yes?
Is the turn-off in its quality always better than the Chebyshev quality?
It is always better if it can be applied. That's the catch. You can't always apply the turn-off inequality, which is why you need to know all of them. But when all 3 can be applied, that's the strongest. Why? Because the tail it gives you is exponentially dropping. It's great. So it's basically Gaussian. Right? The Chebyshev bound is kind of a square curve, it's just linear. So when you can apply it, the turn-off is best. The problem is you need all these extra assumptions to apply it. And that is not. Yes?
So that means if I use the hopping bound, I seem to get a looser bound than the Chebyshev bound doing something wrong.
So that's an interesting situation because there is, at least in the homework, there is a case where that can happen. Just because in the limit the bound is much better, but there's some initial region where it may not, it starts off with the Chebyshev bound slightly better than the Chernoff bound kind of overtakes it. And if you happen to be in the initial region where it's not so great, you might actually see that happening. But eventually it will work. And I suspect that's what you're seeing, because I know there's one thing where that happens. Any other hand? I don't know other hands. Any other? Yes.
Yes. Number 7, the first.
Which of course I remember completely.
It's the de-randomizing
Yes.
by brute force.
Yes. Brute force. Yes.
So are we like?
There's a clue. That's a big clue, by the way. The brute force thing. Sorry. What was your question again?
Well, now you said that's a hint. But I mean like.
That's why I said, and I think I said in the assignment. That's a big hint.
Oh, okay. So are we like assuming that we don't know what's being put into this randomized?
All you know is that the randomized algorithm is some black box. It takes a stream of random bits, which you can see, and it takes the input, which you can see. What it does, you have no clue. You don't know anything about it. It's a black box.
So, sorry, what does it take again?
It takes a stream of random bits,
Okay.
and it takes the input.
So that's your input, is the stream of random.
Well, a randomized algorithm has 2 things, right? It takes random bits and it takes the input itself.
Oh, okay.
You don't know what's going on inside the black box. That's all you can see.
We were talking about, so you put something in.
Well, that's different. I mean, a black box is just all you can see is what goes in and what comes out. But you don't have any access. It's because it's a black box. You can't see inside. It's like a black hole. You don't know what's going on there. A black hole, nothing comes out. That's it. Yes.
So you notice that we have to serve this correctly. So do you mean it's the exact answer? But the thing is random.
I know. That's the point. You're de-randomizing it. You're getting rid of the randomness. How would you do it? That's the question. Yes.
So, with the Chebyshev inequality, you compare a difference between your actual value. So with the Chernoff, can you only compare with a different, like with a factor proportional to the mean in the way you write it out?
No, it's just that's the most convenient way in which you do it. But you can do any kind of difference. It's just that then the mean will actually show up in the exponent as well in a different way. I mean, you can think of that difference as basically epsilon times the mean or some number blah. But if you replace epsilon times mean as blah and you go put in the exponent, wherever it says mean replaced by blah divided by epsilon, you'll get a general bond. It's just a question of, that's the most convenient form in which to express the bond, but that doesn't mean you have to do it that way. It's just a point that the way to think about that expression is that you should rightfully think of your probability or your tail as decaying in units of the mean. That's the way to think about it. Other questions? So I actually, wrote down every single solution to that homework. So I can say that for the most part, if you apply the bounds, the Chernoff, Chebyshev, Markov, and apply them properly, and you sort of go back to the notes and look at what we did in class, what you're looking for will be there. So. You have to look a bit hard. So there's a question back there. 1 second. Okay, yeah, question?
How long did the assignment take you?
Does it matter?
Yes.
Why?
Build the process and
It's a lower bound.
No, but 5 points for whoever said that. Who said that, the lower one? Yes, 5 points for you, just for saying that. I feel happy now. No, I'm not telling you, because it doesn't matter. The time it takes to do the assignment is not the point. Yes, you have to finish it by next Friday. The point is just do it. Speed is not the issue. In case you're all wondering, in my undergrad algebra class, I got a B. I'm not very good at doing things fast. I did not do well on the exams and stuff. That's why I don't have exams in this class. So I'm a very slow person in that regard. But that's okay. Yeah. See, I said this on video now. Everyone in the world knows I got a B. Yes.
questions. Could I ask do you maybe go over like the proof of the Chebyshev a little? Because I looked up the proof about how you apply the Markov bound to the x minus the value, but it seems like they chose sort of these values magically a little.
Yes.
Is that how it is?
That's like the assignment question has been asked. That question I don't remember. Generalized.
Because one of the questions seems sort of similar to that, and so I was trying to think.
It is
if they
similar.
do it this first one, how kind of related to the second? So
Well, the basic, so I didn't prove the Chernoff bound, by the way. The Chernoff bound is also proved by using the Markov inequality. Construct a special random variable, apply Markov inequality to it. Chebyshev is construct a special random variable, apply Markov inequality to it. What I've asked you to do assignment is construct a special random variable, that's what you have to do, apply Markov inequality to it.
Well, what I mean is just the way they applied it before, it sort of seemed like they just picked magic numbers to make things work out, so do we have to pick some magic numbers to make things work out?
Probably. It's not that much magic. It's actually, I mean, like I said, I know the solution. It's not that complicated. And by the way, you're all, I'm assuming you're all expert Googlers. You will find some of these solutions, or at least parts of them, or versions of them on the web. I'm pretty sure of it. You could do that. You will get points. You can, as long as you cite it, and I don't catch you not citing it, you'll probably get the points for it. But you do have to ask yourself if it's going to help you, because as I said, if you don't work these things out now, the next assignment, when you can't Google it, and you didn't know how to do this analysis, you're going to have trouble. So just keep that in mind. Everything is Googleable eventually, so I'm pretty sure that all this will, it took me about, I think, 3 seconds to find all the solutions on the web. I'm not going to tell you which problem it was. so it all can be found, but try at least to do it before you start working on it. You will learn a lot more that way. So, yeah. Now, I've already given up, I've admitted defeat to Google on this matter. I cannot compete with Google's ability to produce answers to any homework I can think of, so. Okay, so no more questions? No? Okay, I will see you next week then. And I have office hours at 1 o'clock.
Yeah, there's probably like 1 day or so.